Okay, so let's go ahead and get started. So the last few weeks we've talked about the high level issues with using GIS in clinical medicine. We've talked about some of the basics of how to drive a GIS and just kind of getting around navigation, etc. Last week when we talked about adding data, and then we last week we talked about starting that process of data linkage, which is ultimately where you want to go, or where a lot of you will want to go. Having that ability to um, identify um, kind of geographic contextual variables that could be influencing the health of your patients. So what we call geomarkers, what my colleagues and I call geomarkers, and it's this growing area of work where we can look at social drivers, environmental drivers, put them all together, link them with patient data, so that you're bringing in this kind of external data that's external to the clinic with internal clinical data to get a more holistic picture of your patients, and with the ultimate goal of patient-centered personalized care for them, so giving them the best care possible. So today we're going to jump in a little bit further and talk more about linking data. Specifically, I'm going to talk about using point data. So this would be what you have for your patients, or so like patient home address, or it could be like clinical data in terms of where locations of clinics are, but it can be other things too. So as you'll see, so we're going to just go ahead and jump into this. Okay, quick review. Covering navigation, reducing, I didn't say this in the review. We talked also about reducing the size of your data, which is really important because, as you've seen already, when you're using the NHGIS and other data sources, you're going to need to be able to bring down that data to a size that makes sense for your computational needs, for what you're able to do for most of you on your laptop. So we talked about the attribute query, or the ability to pull out data based on what's present in the attribute table. So for example, we went through selecting just the state of Georgia from an entire national states data set. We did it with counties, so just pulling out counties in Georgia, etc., and just making your data far more manageable to work with. So that's another thing that we reviewed that's going to be important for you going forward. We've talked about how to use the NHGIS. I cannot stress enough how important it is to practice with this data set. So for those of you, if you have not already done so, sign up, it's free, and start playing with it, because this is where pretty much, well, the vast majority of social drivers of health data are stored for the United States. So because it has access to the US Census data at all of the geographic levels at which you would want to be looking at, back to like the origins of the census, it is a very rich, relatively easy to use data resource when you're trying to look at kind of all of those kind of geomarkers that we've been talking about with patients. So we talked about how to do that, but again, it's just one of those things that it gets better with time, and there's no replacement for just practicing with it. Okay, we pulled all of that data together. We did the data reduction, we did the linkage through the NHGIS in order to create a thematic map or a choropleth map, so that we could actually start to visualize the beginnings of these geomarkers. We looked at, in this example, we looked at the percentage of the population that are classified as urban or rural within Georgia, which is what you're seeing here. We've talked a little bit about how to classify your data. So deciding like, how many numbers of classes do I use? What method do I use to create these classifications? So we talked about how there's a default in a GIS. In this case, in QGIS, it's like a quantile approach. So they're basically putting like an equal number of observations into each bucket, but that isn't always what makes sense for you when you're trying to understand your data. We talked about using natural breaks as a way to classify data based on natural divisions in your data, the natural categories that emerge based on the distribution of your data, but then also that also is not super helpful sometimes when you're trying to present data publicly. So the way that you look at your data when you're just trying to get a feel for it and explore it, can be very different from the way you actually present your data out to the public or even to colleagues. And so we talked about the value of using things like defined intervals, like 10% categories or 20% categories or 25%, just to help the data be more easily digestible for an audience. So that's kind of the very quick run through of where we have been, which brings us to the point today where we can talk about working with point data, going through some basic background and techniques. And specifically, we're going to talk about how to bring in coordinate data and also address data. So both of these approaches end up with points on maps. It's just that the input looks different and there you handle it differently, of course, in the GIS. So just the examples that you have here, XY coordinates, which would be latitude and longitude. That's one way to bring in point data. What's probably more common, at least in the US context, with clinical medicine is that you've got address data that you want to be able to bring into the map and investigate. Okay, so I will tell you that I'm going to start with XY coordinates just because I want to make sure I've said this to you. Sometimes you will use it. If you are working in more of a global health context, you absolutely will need to become very comfortable with this because coordinates are everywhere. So globally, so it's a really standard approach for bringing in data. The geocoding address data, that's very specific to like geopolitical context, like the way our address structures run in the United States is not the same way as other countries. So you get to some more like place-based kind of specific approaches. So I do want to start with the coordinates because it's just something you need to have in your back pocket. One of, I think, the best practice resources for bringing in coordinates is from the Environmental Protection Agency. I have the link down here. They have something called the Toxic Release Inventory, or the TRI data set. So it's basically every business or every facility that uses a substance that is required by law to be monitored by the EPA. They are in this data set. You'll also, just maybe from more of a clinical and environmental health perspective, it has detailed data on carcinogens and how many, like what carcinogens are present in these places, how they may be released. So, are we talking through stacks, other forms of kind of exposure that may be affecting your communities? This is something that I used a lot in my research when I was in grad school in Louisiana, because we have a lot of petrochemical processing and associated plants, which raise a number of environmental health concerns. But going back to just fundamentals, these data, each of them, every one of these facilities has a latitude and longitude. So it's an enormous data set for the entire country, going back for a very long time, but it's coordinate data. So you can really practice with bringing coordinate data into a GIS, which is why I have it here. So before we can go in and work with coordinate data, and really something you need to understand for any use of GIS, it just becomes more apparent when you're working with coordinate data, is this idea of a spatial reference system. Different GISs call it different things and look at it differently, but at the end of the day, it really is just this combination of a datum and a coordinate system. And it affects the way that your map looks, and it affects the way your data comes into the map when you're using coordinates. So we're going to start with just datum. So just bear with me as I just go into professor mode and just give you a little bit of content so that you have this again in your back pocket before you go to apply this in a GIS. So a GIS is obviously presenting a model of Earth. It is not the real thing. It is clearly not a one-to-one relationship. It is not exact in any way. It is a model. And as I'm sure you've heard in other classes, I think it's commonly said with statistics, like all statistical models are wrong, some are useful. All models of Earth are wrong, some are useful. So that applies here as well. So Earth is really a geoid, which is this lumpy thing I have over here on the left, which you can imagine. But when we go to map Earth in a geographic information system, we have to use a model of that really messy, uneven geoid. And that's where Earth gets represented as, we would call it either an ellipsoid or a spheroid. So there are ways to, there are mathematical models that translate that geoid into the ellipsoid. And depending on the datum that's used, it actually, it can squish Earth in different ways. It reconfigures it, and that can actually shape your coordinates and the way your map looks, and the ability, most importantly for you, of your data to overlay each other properly in the correct geographic position. So I'm not giving you anything in our time together that comes from different datums. But just know that if you really go further down this line of working in a GIS, you'll have some data that are derived off of a datum from 1927, some maybe from one in 1983, some from in 1984. And depending on when you get that data, what datum they're using, the data will not align. They'll not necessarily overlay neatly in a GIS. So you kind of just need to know that this is out there, especially if you go further down this path, okay? Now, in addition to, sorry, so here's the real Earth, the geoid, the rounded version model of Earth, and then there's the flat projected map that we're going to do. So you can see there's a lot of translation. There's a lot of decision making mathematically about how we get from point A to point C in this case, okay? All GISs will tell you what the spatial reference system is of the data that you're using. It's usually under properties, and it'll tell you the datum and all the data that we use in what we're working on. It's going to be the North American datum of 1983 or the World Geodetic Survey of 1984. So it's that's pretty much the only two you'll ever see working with me, at least over the course of the summer. Then the next thing we need to consider is the coordinate system. So, and this is going to probably go back to like fourth grade social studies or something for y'all. So apologies if it feels boring, but I do need to just make sure that you that we kind of level set on the kind of numbers that we're looking at here, so you know what's to be expected, and then you can also catch any errors in your data, which does happen. I can't tell you how many times somebody has sent me data from the field when they were out collecting GPS data, and something happens and I get like really weird values, like the latitude of like, I don't know, 176. Well, latitude only goes positive 90, negative 90. So when I see a number like that in the latitude, I know that there's an error, usually a flip-flop in latitude and longitude, but still, you just kind of need to know what the norms are for the values you should expect. So the coordinate systems that you'll see, the coordinate data that you'll see will range from 0 to 90, representing the northern hemisphere, in the latitude, and then 0, of course, equator to negative 90 for southern hemisphere. So of course, if we're doing work in Georgia, we know that we are going to have a positive latitude value. Same thing with longitude, measuring east and west, from 0 to 180 and then 0 to negative 180. In the United States, of course, we are going to be in that, and you can see from this model here, we are in negative latitude, negative longitude location. So in Georgia, you can expect to have a positive value for the latitude and a negative value for the longitude, okay? So sometimes, and this is just based on, again, just round Earth, right, that ellipsoid. Sometimes there will be reasons why the data get flattened or projected, and that can affect the way that it's visualized, but that's not anything we're dealing with at this point, just to know that it's out there, and we may come across it. This is just an example of like why it matters that you pay attention to your datum and your coordinate system. So this example here over on the left, this is actually three different ways of three different spatial reference systems, basically, of the same data. And you can see that depending on the way you, depending on its origins and how it was designed, it can look slightly different, and it can cause data to not overlay properly. Okay, so again, for us, we're probably working with the North American datum of 1983 or the World Geodesic Survey of 1984, the WGS 84, and that's pretty much and just geographic coordinates. We're not going to do anything beyond that. Always fun, I think, to use Google Earth to just reorient yourself to what are the expected coordinates that you could have depending on your study area. Um, and then one thing that you really do have to keep in mind in a GIS is that when we talk, so this is translating from kind of global coordinate systems into how a GIS reads them. When we're talking about latitude and longitude, just conversationally, we tend to say that like X is our latitude, right? Because it's how we go north or south of the equator. But in a GIS, X is thought of as the X axis. Okay, so think about, a Cartesian plane with an x-axis and a y-axis. A GIS, when you say X to a GIS, it thinks, oh, you mean the x-axis. So when you move along the x-axis, you're not changing latitude, you're changing longitude. Okay, so just keep it in mind. It's flipped in a GIS. So the X field in a GIS, when it's asking for an X field, when you're bringing in coordinate data, it's actually asking for the x-axis field, which is going to be your changes in longitude. So same thing then, in a GIS, the y-axis, and when we're just talking about latitude and longitude, X is latitude, Y is longitude, but in a GIS, Y, when it's asking for y-axis or y data, it's asking for y-axis data. And so as you move along the y-axis, you're actually changing your latitude, right? North or south of the equator. So it's flipped. So this is a really common mistake, not just in folks who are new to GIS, but even people who've been using GIS for a long time. It's such a flip-flop mentally of what you would say and then the way the GIS actually reads it. So it's something to keep in mind, okay? So you're not going to do this right now, but this is just practice for you moving forward. One of my favorite ways to start to learn how to bring in coordinate data into a GIS is to do this via Google Earth, and specifically Google Earth Pro for desktop, so not the web version. Only because, sorry, I've been down here at the med school since 7 o'clock this morning, so I think I'm just starting to yawn. But not only because it allows you to actually go in and grab coordinate data as if you were in the field, but also as you'll see later on that we can actually use Google Earth Pro to digitize or draw features in a map, and that can be read by a GIS. So actually Google Earth Pro Desktop and GISs, they can speak each other's language, basically coding language. And so whatever you do, or a lot of what you can do in Google Earth Pro Desktop from a mapping perspective can be brought into a GIS. And then what you do in a GIS can actually be written out to Google Earth Pro Desktop, which is really great because, most clinicians aren't going to have, most physicians don't have GIS, but Google Earth Pro Desktop, it's free. And really like platform neutral. And so if you can create some of your data and maps in a GIS, you can save it out as a Google Earth Pro file, and you can go wherever to do your presentations and be able to share your data. You can also zoom around and zoom into the satellite imagery, aerial imagery as well to just get some more context for what you're looking at. So for practicing with this data, this is a really valuable resource, Google Earth Pro Desktop. So I have the details here. And then something to pay attention to when you go into Google Earth Pro Desktop is if you go to the Tools tab and Options, you want to go down and you want to change the latitude and longitude formatting. So this is key for a GIS. So latitude and longitude, as you probably learned it in school, at least the way I learned it in school, it would be like 90 and then like a degrees symbol and then the letter N to say 90 degrees north for the North Pole. A GIS, as you might have already figured out, really doesn't like all those special characters and that level of kind of inconsistency in formatting. It really likes decimals and just positive, negative values. So whereas you probably learned, or I certainly learned, latitude and longitude in what's called degrees, minutes, seconds format, the GIS likes it in what's called decimal degrees. So you'll go and you're going to change it to decimal degrees. So you get rid of that degree symbol and you get rid of the letter. So everything's just positive and negative decimal values. Okay. Now, the coordinate data are shown in the bottom right-hand corner of Google Earth. So you can download it and start to zoom around. And you'll notice that as you move around, you're also going to see the coordinates change. Oh, here we go. My early start this morning making me yawn. So you're able to then, whatever you observe as your coordinates in that lower right-hand window of Google Earth, you can actually basically copy paste or transcribe them across into an Excel file or a spreadsheet file. So just as a really quick example for me, I do this with my GIS classes here. I always just do like, okay, my favorite places to eat when I go home. And it just teaches us how to format data so that it's GIS readable. So I zoom into my three of my favorite places. So I zoom into Dinglewood Pharmacy, if anybody's been there and had the scrambled dog. I love a scrambled dog. So Dinglewood Pharmacy, and I'll grab the coordinates. I also love the Smoky Pig barbecue. So I put Smoky Pig and I zoom into it in Google Earth. I write down its coordinates. And then I love the country store at Callaway Gardens in Pine Mountain. So I'll go to the country store in Google Earth, and then I will type in those coordinates. So again, it's just going to give you that practice of like what coordinates look like, and specifically what they look like in a GIS. And again, notice here, I'm not using any degree symbols or letters. It's just positive and negative values. And notice that latitude, at least for Columbus-ish, Georgia, is around 32 degrees north and about 84 degrees west, okay? Also notice that because I know I commonly also flip-flop the X and Y conversion into a GIS, I don't call my fields X and Y for latitude and longitude. I actually write LAT, sorry, for latitude and LON for longitude. And that way, when the GIS is asking for these data, when it's asking for the X value, I put in the longitude. And where it's asking for the Y value, so again, moving along the y-axis, I put in the latitude, and it just helps keep me clear. So I have this for y'all. You know, again, we're not going to do it right now, but I have it for you to go and practice with later. So it can be, I've also done this with like favorite like SEC stadiums. So you can kind of zoom to the middle. Mine is obviously Tiger Stadium in Baton Rouge. Don't boo me. But anyway, go to the middle of the stadium, write the coordinate. Same thing, you know, on and on and on and on. It's just kind of a fun way to practice with coordinate data. And then we can talk about like how to bring those in, and I'll show you that in just a second. Okay, so let me pause here and ask if there are any questions. And again, knowing that I can't see all of your faces because it's a screen share. Anybody have anything about coordinates? Okay, so how do you bring them in? So this is, again, so we've talked about using the vector data. We've also talked a little bit about that raster is not something we're using at the moment, but the delimited text is another way to bring in data. We've brought in delimited text when we brought in those data tables from the NHGIS, but those data tables did not have any geometry to them. So if you look at this, what we're doing is we're bringing in delimited text. I have the file at the top. These are my practice coordinates that I created out of Google Earth. And then I'm not really going to be dealing with anything else. I'm leaving it all as the default until geometry definition. So if you recall, when we worked on linking data from the NHGIS, the little radio button we had pushed was no geometry, attribute only table, right? Because it just had like data on the percentage or the number of people who are classified as rural or urban. Here, though, we do have point coordinates. So we do have a geometry. And here you can see what I was talking about. The X field it's asking for, it should read it by default, but in case you have to actually tell it, the X field is going to be longitude. The Y field is going to be latitude. We do not have ZNM fields, so you don't have to worry about it. And you can just leave the geometry. This CRS is your spatial reference system. It should pick up that it's this WGS 84, World Geodetic Survey 84. If it doesn't, though, you can just select it from the drop-down menu. And then down at the bottom, it gives you under sample data, it gives you a preview. And sure enough, you can see that my data came in properly. Okay, so once that happens, you can just say add, and you can see that it's in my map now, right? It's in my GIS. So I have down at the bottom, that's going to be Dinglewood and Smoky Pig down in Columbus. And up at the northern part of the view, that's going to be the country store in Pine Mountain. Now, because this is in your GIS, now you can bring in all of those social drivers data that are available in the NHJS. So although we use the example of like places I like to eat, you can imagine this could be clinical data. So like locations of clinics, locations of other healthcare resources. It could be patient locations. It could be, some of that data I just briefly previewed for you, like the toxic release inventory data, if you wanted to look at like environmental risk around your patients, et cetera. So that is one way to bring in point data into your GIS, and that is using coordinates. Okay, so before we move into geocoding, are there any additional questions? Okay, the last thing we'll cover then is geocoding, and we're not going to go all the way into it. We're just going to touch that. There's like people who do full PhDs on this, but basically we're taking address data and we're basically finding where these addresses are along street networks. Okay, so whereas coordinate data doesn't require a street network, a geocode does. It's basically a proportional, it's going to assign the proportional location to like if you have 100 Main Street and 200 Main Street, the address 150 Main Street, the GIS will pop it right in the middle of that line segment. So you have this here. Okay, so really, really simplistic, but there's a lot behind it. Okay, and again, if you have an address table and you have some form of road shapefile or access to like Google Maps, there are a variety of ways to get this done, but you have to have some reference file like roads in order to do it, okay, to tie these addresses to the location on the road. I'm not going to get into some of the details with the road file just because you don't actually use it so much anymore, and you'll see why in a minute. We tend to either use OpenStreetMap or Google Maps for geocoding unless it's patient data. If it is your patient's addresses, you do not pop that out into the cloud for geocoding. There are behind firewall ways to do that, which we can talk about on a case-by-case basis, because depending on where you are with your patient data, it's going to look a little different. So we're going to handle just geocoding from like a high level, publicly available perspective. There is a paper that I have linked here for you. I'm not going to go into all of it. Sorry, let me get back, from Jeff Jacques, and it is old now. It's quite old, but I will tell you that it's a classic, and these assumptions that we make hold still. We make a lot of assumptions when we go to geocode our patient data. For those of you who are working with me on the post office box project, one of those assumptions is that our patients have an address that's even geocodable, which not everybody does, and certainly not in rural places. So we make that assumption. We make some assumptions about how accurate or how close we can get to the map to the actual location, which again, depending on urban or rural or suburban areas, could be different. But you have these references here for your reading that I've placed at the bottom. And this one I really like too, because it shows you that there are so many different ways to geocode your data, depending on the resources available to you and what your aims are. So this is called positional accuracy. How close do we get to the actual location? And this is just the reminder that not everybody geocodes. Or not every patient's address can be geocoded. So this is a paper from, again, old, 2005, but notice here at the bottom, Matthews, the author, that's Dr. Kevin Matthews from the Centers for Disease Control and Prevention, who's my colleague, and he's speaking to you either next week or the following week. So, and he runs the Office of Rural Health for the CDC. So he's been thinking about these issues for a long time and is really looking forward to talking to you about just the data quality and kind of things you can do from a rural health perspective with the GIS. Also, always keep in mind that whenever we geocode or use coordinate data, we're treating this as like a static point on a map. And if we're talking about our patients, they actually move quite a bit. So they move addresses that can change over time. Even over the course of the day, they're moving. So there are other ways to think about how we link their social and environmental drivers than just the home address, but that's where we're starting with, okay? So again, for practice for you, I'm just doing the same thing I did before with the same places, but instead of coordinate data, I'm putting the addresses in. So Dinglewood Pharmacy, Smoky Pig in the Country Store. I looked up their addresses. And this is the way you set up a file for geocoding in a GIS. You'll have an ID, a name, an address, city, state, and zip. Okay, and they're all separate here. They're in separate fields. So in the GIS, QGIS, if you're using Arc Pro, it's less steps. Some of the stuff is built in, but in QGIS, you have to load a plugin for geocoding, and it's called MMQGIS, which is easy to just plug in and say run. And then when you go, it should pop up at the top of your view. And if you go to MMQGIS, you go down to geocode, and you're going to geocode a CSV file, which is what you just created, in Excel, basically. It's going to ask you for the file, and then the things I just said, address, city, state. And then the web service, I'm going to use OpenStreetMap because that's easy to do. And it's where I recommend you start with this. It's going to give you an output file name. And then equally important, you'll see a not found output list. So not every address will geocode, and it is as important to look at what does not geocode as what does geocode, because you're excluding some data when they don't geocode, and there are ways to go back and fix it.